Welcome to our deep dive into the question, could the Megalodon still exist today? We'll separate fact from speculation using the latest paleontology and marine biology to explore this ancient predator and why it continues to capture imaginations worldwide. Comment where you are in the world and what time you're seeing this. The Megalodon was a real scientifically documented shark that once ruled the oceans as the largest predatory fish in Earth's history. Size estimates drawn from fossil teeth and rare vertebral evidence place adults at lengths of 50 to 60 feet, with some calculations reaching as high as 65 feet for the biggest specimens. A single tooth could measure more than 7 inches from root to tip, roughly 3 times longer than those of today's great white sharks, and the spacing of preserved vertebrae suggests a massive barrel-shaped body weighing up to 60 tons or more. These measurements come directly from comparing tooth proportions and spinal column segments to living shark species, giving researchers a reliable if still approximate picture of its true scale. Physically, Megalodon possessed a robust, torpedo-like frame with a powerful caudal fin for bursts of speed and enormous pectoral fins for maneuvering. Its jaws spanned nearly 10 feet across when open and contained row after row of serrated triangular teeth designed for slicing through flesh and bone. Unlike modern sharks that often rely on speed or stealth alone, Megalodon combined immense size with bone-crushing bite force estimated at over 40,000 pounds per square inch. It differed from contemporary species in its thicker, more heavily calcified vertebrae and broader, less streamlined head shape, adaptations that supported a lifestyle as an apex hunter rather than a pursuit predator. Evolutionarily, Megalodon belonged to the extinct genus Otatus and first appeared around 23 million years ago during the early Miocene epoch. It dominated marine ecosystems for nearly 20 million years before disappearing in the Pliocene roughly 3.6 million years ago. During its reign, it occupied the top of the food chain across multiple ocean basins, outcompeting other large sharks and marine mammals alike. Fossil records show its presence from the warm shallows of what is now Florida and Peru to deeper coastal waters off Australia and Europe, indicating a preference for temperate to tropical habitats where prey was abundant and water temperatures stayed above roughly 12 degrees Celsius. Its diet centered on large marine mammals, especially early whales such as cetotheres and squalodons, along with seals, sea turtles, and even other sharks. Bite marks on fossil whale bones match the size and serration pattern of Megalodon teeth, confirming it could disable prey much larger than itself by targeting flippers or tails before consuming the carcass. This predatory strategy required vast energy reserves, which its massive size helped supply through efficient heat retention and opportunistic feeding on whatever megafauna shared its range. Geographically, Megalodon enjoyed a near-global distribution, with teeth recovered from every continent except Antarctica. It favored productive coastal and shelf environments rather than the open ocean, thriving where nutrient upwellings supported dense populations of marine mammals. This wide but habitat-specific range underscores how closely its survival was tied to stable, prey-rich ecosystems. Although often compared to the great white shark, Megalodon is not a direct ancestor. The two belong to separate evolutionary lines within the mackerel shark order, with the great white tracing its roots to a different branch of the Carcharodon lineage. Megalodon's closest living relatives are actually the smaller mako and porbeagle sharks, a distinction confirmed by tooth morphology and molecular clock studies of living species. Understanding these differences keeps the Megalodon grounded as a distinct prehistoric giant, rather than a simple oversized version of animals we see today. Building directly on the Megalodon's impressive adaptations and global reach that we explored earlier, it's natural to wonder how such a dominant predator could simply vanish from the oceans. This section of our deep dive into whether the Megalodon could still exist today examines the scientific timeline and causes behind its extinction, grounding everything in fossil evidence and paleoclimate data, while acknowledging the fascination with the idea of a hidden survivor. As always, comment where you are in the world and what time you're seeing this. The fossil record places the Megalodon's final confirmed appearances between roughly 3.6 and 2.6 million years ago. marking the end of its long reign that stretched back to the early Miocene. Teeth and occasional vertebral remains from sites in the southeastern United States, Peru, Australia, and parts of Europe show a gradual tapering off rather than an abrupt disappearance, with the youngest reliably dated specimens clustering near the close of the Pliocene epoch. This time frame aligns precisely with the broader Pliocene marine extinction event, a period when numerous large marine vertebrates disappeared amid shifting environmental conditions across the world's oceans. Scientists date these last occurrences using radiometric methods on surrounding sediments and biostratigraphy tied to other index fossils, providing a solid consensus that Megalodon did not persist into the Pleistocene or beyond. Multiple pressures converged to drive this extinction, beginning with widespread climate change that cooled ocean temperatures. As the Pliocene progressed, Earth entered a phase of intensifying glaciation, with expanding polar ice caps drawing down sea levels and lowering average water temperatures in many regions below the roughly 12 degrees Celsius threshold that Megalodon appears to have preferred. Fossil distributions indicate the shark favored temperate to tropical coastal zones, and cooling would have compressed those habitable ranges, forcing individuals into smaller, less productive areas. This wasn't a sudden freeze, but a progressive shift that stressed the shark's physiology over thousands of generations, reducing metabolic efficiency and reproductive success in what had once been stable environments. Compounding the cooling was a sharp decline in the Megalodon's preferred prey species. Large baleen whales and other marine mammals that had flourished earlier in the Miocene began to dwindle as nutrient cycles changed and upwelling patterns shifted with the new climate regime. Bite mark evidence on whale fossils shows Megalodon relied heavily on these megafauna for sustenance, and their reduced numbers meant the energy demands of a 50 to 60-foot predator could no longer be met consistently. At the same time, competition intensified from emerging rivals such as great white sharks and early orcas, both of which evolved more agile hunting strategies suited to the cooling seas. Great whites, with their own lineage tracing back through different mackerel shark ancestors, began occupying overlapping niches, while orcas developed sophisticated pack hunting behaviors that allowed them to target similar large prey more efficiently than a solitary megalodon could manage. Another critical factor was the loss of coastal nursery habitats essential for juvenile survival. Megalodon young likely depended on shallow, protected embayments where smaller prey abounded and larger predators posed less threat. Pliocene sea level fluctuations and cooling-driven habitat fragmentation eliminated many of these refuges, increasing mortality rates among the next generation before they could reach maturity. This habitat squeeze operated alongside the other stressors, creating a cascade effect where adult populations aged without sufficient recruitment. Taken together, these elements formed a classic case of extinction through synergistic pressures rather than any single catastrophe. The Pliocene marine extinction event provides context for this pattern, as similar declines struck other apex predators and large vertebrates when climate, prey bases, and competition realigned simultaneously. Mainstream paleontology views this as the verified explanation supported by stratigraphic, isotopic, and ecological data, without room for survival into modern times based on current evidence. That said, the same climate dynamics we see documented in ancient sediments offer a timely parallel to today's rapid ocean warming, reminding us how sensitive large marine species remain to environmental shifts even if the specific triggers differ. Exploring these factors also highlights why speculation about hidden megalodon populations persists in popular imagination despite the scientific timeline. The sheer scale of the animal invites questions about whether some deep ocean refuge might have allowed a few individuals to persist unnoticed, yet the documented contraction of suitable habitats and prey leaves little ecological space for that scenario under consensus models. By examining the extinction through multiple lines of evidence, we can appreciate the megalodon's story as a complete chapter in Earth's history while staying grounded in what the fossils actually reveal. This understanding sets the stage for evaluating other claims we'll examine next. Continuing our investigation into whether the Megalodon could still exist, this section confronts the central challenge posed by the fossil record itself, weighing what the preserved evidence can and cannot tell us, while keeping the door open to speculative possibilities that some viewers find compelling. Comment where you are in the world and what time you're seeing this. The same extinction pressures we just reviewed left behind a clear stratigraphic signature. Yet that signature is incomplete by its very nature. Shark skeletons are composed almost entirely of cartilage, a material that decomposes rapidly and mineralizes only under exceptional conditions. Unlike bony fish or marine reptiles whose vertebrae and skulls routinely enter the fossil record, Megalodon left behind almost nothing but its teeth, the only hard parts durable enough to survive millions of years of burial and uplift. This bias means our picture of the species rests overwhelmingly on dental remains scattered across shallow marine sediments from the Miocene and Pliocene. Those teeth appear in predictable geographic patterns, concentrated along ancient coastlines of what are now the southeastern United States, Peru, Australia, Japan, and parts of the Mediterranean, reflecting the shark's preference for productive temperate to tropical waters. Their abundance in older layers gives way to a progressive thinning, with the youngest well-dated specimens clustering between 3.6 and 2.6 million years ago. After that point, the record simply stops. That abrupt cutoff carries weight precisely because teeth are such durable markers. A single 50-foot megalodon would shed thousands of teeth over its lifetime, many of them large enough to be spotted by beachcombers or dredged up by fishing nets. If even a small population had persisted into the Pleistocene or Holocene, we would expect at least occasional specimens in younger sediments or in modern seafloor deposits. Their absence is therefore meaningful, not merely an artifact of poor preservation. Marine fossil records do contain gaps, especially in the deep ocean where sedimentation is slow and retrieval difficult. But Megalodon's inferred ecology, centered on productive coastal and shelf environments where fossil recovery is comparatively good. The lack of post-Pliocene teeth in those well-sampled zones cannot be dismissed lightly. Still, the incompleteness of the record invites comparison with genuine Lazarus taxa. The coelacanth, once thought extinct since the Cretaceous, resurfaced in 1938 off South Africa and again in later decades in deep Indonesian waters. Other examples include the Wallamai pine and the Laotian rock rat, species that vanished from the fossil record for millions of years only to be rediscovered alive. These cases demonstrate that absence of evidence is not always evidence of absence, particularly for organisms living in remote or deep habitats that rarely contribute to the sedimentary archive. Megalodon, however, differs in critical respects. It was an apex predator exceeding 50 feet, far larger than any living shark, and its metabolic demands would have required regular access to large prey in relatively shallow zones. A hidden remnant population would need to evade not only fossilization but also every modern survey method, from trawling to sonar mapping to underwater cameras. That combination of size, ecological footprint, and survey effort makes direct analogy to the coelacanth imperfect. What would actually constitute proof of modern survival? A single verified tooth embedded in a sediment core dated to the last few thousand years would reopen the question, as would DNA sequences recovered from seawater or stomach contents of known predators that match Megalodon genetics. High-resolution video or tissue samples from a living individual would, of course, settle the matter definitively. None of these lines of evidence have appeared despite decades of targeted deep-sea exploration and widespread recreational diving. Claims occasionally surface of oversized teeth found in recent sediments, yet every examined specimen has proven to be reworked from older strata or misidentified. Such negative results do not close every theoretical loophole, but they tighten the constraints around any survival scenario. The marine fossil record's limitations further complicate interpretation. Deep basins and hadal trenches preserve few vertebrate remains because of low sedimentation rates and aggressive scavenging. If a relict megalodon population had retreated entirely to these remote realms, its traces might remain hidden for a very long time, yet the same physiological constraints that shaped its extinction, notably a preference for water temperatures above roughly 12 degrees Celsius and dependence on large energy-rich prey, make such a retreat improbable. The deep sea offers neither the thermal stability nor the megafaunal biomass required to sustain even a handful of such giants. While gaps undeniably exist, they are not uniformly distributed across all ocean depths and latitudes, and the specific niches Megalodon once occupied are among the best sampled in the entire paleontological archive. Taken together, the evidence presents a coherent picture, a species whose last confirmed remains coincide with well-documented environmental upheaval, whose primary fossil signature disappears without trace in younger strata, and whose biology renders prolonged concealment in unsampled habitats unlikely. At the same time, the inherent biases of cartilage preservation and the existence of other Lazarus taxa remind us that surprises remain possible in the vastness of the ocean. Future discoveries could alter that assessment, but until positive evidence emerges, the fossil record continues to weigh heavily against the idea of a living megalodon. This assessment now directs our attention to the next critical factor, the question of whether any part of the modern deep sea could actually support such an animal. In this section of our journey, asking whether the megalodon could still exist, we turn from the fossil record's silence to the one place some viewers hope might still hide a living giant, the deep ocean. We will weigh the real biological barriers against the slim but intriguing possibility of adaptation, all while keeping the conversation grounded in what marine science actually tells us. Comment where you are in the world and what time you're seeing this. The deep ocean remains one of the least mapped environments on our planet. Less than 10% of its floor has been surveyed at high resolution, and entire mountain ranges, trenches, and mid-water zones stay effectively unseen by human eyes. That vast unknown naturally invites speculation. After all, new species continue to appear in scientific literature every year, sometimes from depths that were once considered too hostile for large vertebrates. The discovery of the Indonesian coelacanth population in the late 20th century, the ongoing finds of bioluminescent sharks, and the recent descriptions of new chimera and gulper eel species all remind us that surprises still surface. Yet the same data that document these discoveries also reveal consistent physical and ecological patterns that make a megalodon-sized survivor far more difficult to accommodate than a modest deep-water fish. Could a remnant population have retreated into the bathyal or abyssal zones after coastal conditions deteriorated? In theory, the idea is worth testing, because a handful of large predators do occupy those realms today. The six-gill shark, the sleeper shark, and the blunt-nosed six-gill all descend below 1,000 meters and can exceed 5 meters in length. Their existence proves that size alone does not bar an animal from deep water. The question is whether a 50-foot regionally endothermic macropredator like Megalodon could make the same transition without fundamental changes to its physiology and hunting strategy. Pressure presents the first hard constraint. At 2,000 meters, the ambient pressure exceeds 200 atmospheres. Modern deep-sea sharks manage this load through specialized swim bladders or by maintaining neutral buoyancy with large oil-filled livers, and their skeletons remain relatively light. Megalodon's skeleton, inferred from its teeth and fragmentary vertebrae, belonged to a coastal species whose body plan emphasized speed and power in warmer, shallower water. Its cartilage would have lacked the reinforced calcification seen in some deep-sea elasmobranchs, and its large dorsal fin and tail would have generated problematic drag and structural stress under constant high pressure. While cartilage can adapt over evolutionary time, the shift would require thousands of generations of selection, not a rapid behavioral retreat within the last few million years. Temperature adds a second barrier. Megalodon's fossil distribution tracks warm temperate to tropical surface waters, and its inferred metabolic rate relied on regional endothermy that kept swimming muscles warmer than the surrounding sea. Below roughly 800 meters, water temperatures stabilize near 2 to 4 degrees Celsius year-round. Maintaining elevated muscle temperatures in that environment would demand a prohibitive increase in caloric intake. precisely when prey density drops sharply. Living deep-sea sharks avoid this problem by adopting lower metabolic rates and slower lifestyles. They are ambush or scavenging specialists, not active pursuit predators of large marine mammals. Prey availability tightens the noose further. The deep scattering layer and the sparse bathypelagic zone support a food web built largely on detritus and small crustaceans. The largest reliable prey items are giant and colossal squid, which themselves reach lengths of 12 to 14 meters and live at depths between 300 and 2,000 meters. These cephalopods offer an instructive comparison. Their bodies are mostly soft tissue and water. They achieve great size through low metabolic demand, ammonia-filled buoyancy chambers, and a lifestyle that avoids sustained high-speed swimming. A megalodon attempting to subsist on squid would face two insurmountable mismatches. First, its jaws and teeth were adapted for shearing through the thick blubber and bone of whales and large fish, not for the slippery, low-yield flesh of cephalopods. Second, even if it could catch them, the energy return per squid would fall far short of the thousands of kilograms of high-calorie food a 50-foot shark requires daily. Giant squid populations are already thinly distributed. Removing enough of them to sustain even a small number of megalodons would collapse the local ecosystem within years. Some viewers point to the colossal squid's very existence as proof that megafauna can hide in the deep. That argument overlooks the profound physiological gulf between an invertebrate and a vertebrate apex predator. The squid's 3 hearts, blue copper-based blood, and jet propulsion system evolved over hundreds of millions of years for exactly these conditions. Megalodon would have needed comparable wholesale redesigns of its circulatory, respiratory, and sensory systems. No transitional fossils or living analogs suggest such a transformation occurred. Still, the possibility deserves a fair hearing. If a handful of individuals had shifted to scavenging whale falls or ambushing the occasional deep-diving elephant seal, could they have eked out an existence? The numbers argue against it. A single adult megalodon is estimated to have required roughly 2,000 kilograms of prey per day. Even optimistic models of deep-sea biomass show that sustaining 10 such animals would demand an area the size of several ocean basins, with essentially no overlap in foraging ranges. Modern acoustic and camera surveys across those basins have yet to record any signature consistent with an animal that size. More importantly, the same surveys routinely detect much smaller deep-sea sharks and squid, demonstrating that detection itself is not impossible. The fascination with a hidden monster shark is understandable. It taps into our sense of wonder about the ocean's remaining blank spaces, yet respecting that wonder also means respecting the constraints that marine biology places on large, warm-bodied predators. The deep sea is not an empty warehouse waiting to be filled. It is a low-energy, high-pressure environment whose residents have evolved accordingly over deep time. Megalodon's documented anatomy and inferred ecology sit outside those adaptations. That biological mismatch brings us directly to the next question the survival hypothesis must answer. Even if a megalodon somehow reached the deep sea, what would it actually eat on a sustained basis, and would the available prey support a breeding population? Now that we've considered whether the deep ocean could shelter a megalodon-sized survivor, we turn to the most unforgiving constraint of all: the sheer volume of food such a predator would require every day. In this section, we'll examine the caloric needs of a 50-ton macropredator, the prey densities necessary to meet them, and why modern marine ecosystems show no trace of an undetected giant. Comment where you are in the world and what time you're seeing this. A 50-ton megalodon would have needed roughly 2,000 kilograms of high-calorie prey daily simply to maintain basic functions, based on allometric scaling from living white sharks and orcas adjusted for its estimated mass and regional endothermy. That figure rises sharply once we factor in growth, reproduction, and the energy cost of sustained cruising at speeds required to hunt large, fast whales. Marine biologists calculate that an active warm-bodied shark of this size would burn through energy at a rate comparable to a small pod of killer whales, yet without the social hunting efficiency those cetaceans enjoy. The math is straightforward. Every additional ton of body mass multiplies daily intake demands, and Megalodon's fossil teeth indicate a diet centered on marine mammals whose blubber delivered the dense calories needed. Such intake cannot be met by scattered deep-sea squid or occasional whale falls. Prey density must remain consistently high within a realistic foraging radius. Models of shark home ranges suggest an individual megalodon would need to patrol hundreds of square kilometers weekly, encountering large whales or equivalent biomass at intervals of days rather than months. Modern whale populations, however, are both mapped and modest. Comprehensive surveys by the International Whaling Commission and NOAA place global numbers of great whales in the low hundreds of thousands, with most species concentrated along predictable migration corridors and feeding grounds that have been monitored for decades. These animals are routinely photographed, tagged with satellite transmitters, and counted from aircraft. Gaps large enough to hide even a handful of 50-foot sharks do not exist in the data. Distribution compounds the problem. Baleen whales aggregate seasonally in polar and temperate waters where productivity peaks, then disperse across vast oceanic basins. A megalodon relying on these pulses would have to follow the same routes, yet acoustic arrays and long-term sighting databases record no unexplained gaps or sudden local depletions that would signal an apex predator operating outside known food webs. Instead, documented mortality events, entanglements, ship strikes, and disease account for nearly all observed whale deaths. No carcasses display the massive, cleanly sheared bite marks that Megalodon's serrated teeth would leave. Forensic examinations of stranded whales routinely identify orca predation or human causes instead. The absence of such signatures matters because an undiscovered superpredator cannot remain invisible at the ecosystem level. Large sharks restructure prey behavior, whales shift migration timing, reduce time spent at the surface, or avoid certain depth strata. These changes appear in population models and tagging data within a single generation. Moreover, the metabolic waste and occasional predation attempts would alter nutrient cycling and scavenger dynamics in measurable ways. Camera traps on whale falls, for example, already catalog every species that arrives. None include an unknown 50-foot elasmobranch. If megalodons persisted, their presence would register as consistent, statistically significant deviations from expected biomass removal rates, deviations that decades of fisheries-independent surveys have simply not recorded. Some might argue that a few stealthy individuals could scavenge without detection, yet the caloric threshold rules this out. Even optimistic estimates of deep scattering layer biomass fall orders of magnitude short of sustaining a breeding population of warm-bodied giants. 10 adult megalodons would collectively require 20 tons of prey daily. Sustaining that intake across generational timescales would collapse local food chains long before human observers arrived. The same logic explains why no other undiscovered apex predators of comparable size have emerged from modern oceans. The energetic and ecological footprints are simply too large to conceal. This food web accounting returns us to the central tension in the survival hypothesis. While the ocean still holds surprises, those surprises are overwhelmingly small, slow metabolism species adapted to low-energy environments. A megalodon's physiology and diet place it squarely outside that category, demanding resources that would leave unmistakable, and so far absent, signatures across entire ocean basins. That ecological reality now leads us to examine the scattered eyewitness claims that continue to fuel speculation. In this video exploring whether the megalodon could still exist, we sift through paleontology, marine biology, and eyewitness accounts to separate fact from enduring speculation. Comment where you are in the world and what time you're seeing this. Building directly on the ecological barriers we just examined, the absence of any detectable food web disruption makes the survival of a 50-ton predator even harder to reconcile with the scattered reports that continue to circulate. Those reports deserve careful attention precisely because they tap into a deep human fascination with the possibility that something enormous still prowls the seas. We will examine historical accounts of giant sharks, weigh modern eyewitness statements and their inherent limitations, revisit the well-known 1918 lobster fisherman story, consider how documentary dramatization shape public perception, review common cases of misidentification, and close by underscoring why extraordinary claims ultimately require extraordinary evidence. Stories of colossal sharks reach back centuries. 17th and 18th century sailors logged encounters with dorsal fins taller than a ship's rail, or with creatures that dwarfed the largest known whales. Some of these descriptions appear in ship logs from the Pacific and Indian Oceans, where crews described triangular teeth the size of a man's hand washing up after storms. While many of these narratives blend observation with the exaggeration common to long voyages, they establish a pattern. People at sea have long reported animals larger than any recognized species. Marine historians note that such accounts often coincide with periods of heightened whale abundance, when large predators would logically have been drawn to the same prey concentrations. In more recent decades, the reports have shifted from handwritten logs to phone videos and social media posts. Fishers, divers, and coastal residents occasionally describe a massive, blunt-headed shark cruising just beneath the surface, or breaching with a whale-sized splash. These sightings cluster in regions with heavy marine traffic. The waters off South Africa, Eastern Australia, California, and parts of the Caribbean. Reliability varies widely. Many observers are experienced mariners who know the difference between a known species and something unfamiliar. Yet the ocean surface distorts scale, distance, and shape. A fin only a meter high can appear far larger when viewed through spray or at an oblique angle. Lighting conditions at dawn or dusk further complicate judgment, and adrenaline during an unexpected encounter can stretch perceived size. Psychological studies of eyewitness testimony in other contexts show that even trained observers fill gaps with expectations. When the expectation is a legendary giant shark, ordinary anomalies can be interpreted accordingly. One of the most frequently cited modern accounts comes from 1918, when a group of lobster fishermen working the waters near Port Stephens, Australia, reported losing an entire line of traps to a single enormous shark. According to their statements, the animal was long enough to stretch across the full length of their vessel and possessed a head as big as a horse. The fishermen described the shark lifting multiple heavy timber traps from the seafloor and carrying them away. No physical evidence, such as a fragment of trap or a recovered tooth, was preserved, and the story reached print only after several retellings. While the men were locally respected and familiar with the usual suite of local sharks, the lack of corroborating material leaves the incident in the realm of compelling anecdote rather than verified observation. Similar single witness or small group stories surface every few years, yet none have produced the tangible proof, photographs, tissue samples, or unambiguous sonar tracks that would elevate them beyond curiosity. Documentary programs have amplified these stories for new audiences. Productions that blend dramatic reenactments with interviews often present the 1918 account or more recent diver reports as open questions, sometimes overlaying computer-generated imagery of a megalodon-sized silhouette. The visual power of such reconstructions lingers even when the accompanying narration acknowledges the absence of conclusive data. Viewers may remember the image of a massive shadow more vividly than the caveats that follow, contributing to a feedback loop in which dramatized possibilities begin to feel like supporting evidence. This phenomenon is not unique to shark documentaries. Similar patterns appear in coverage of other marine mysteries. The result is not deliberate deception, but an understandable emphasis on narrative tension that can blur the line between speculation and established fact. Misidentification offers another lens on the same reports. The ocean contains several species capable of impressive size and occasional startling behavior. Basking sharks, when seen from the side or with their mouths agape, can appear far more menacing and proportionally larger than their typical 15-meter maximum. Whale sharks, though filter feeders, occasionally swim near the surface in ways that emphasize bulk. Even great whites, when viewed without clear reference objects, can seem outsized, especially if only the dorsal fin or tail is visible. Submerged logs, floating debris, or the wakes of fast-moving vessels have also been mistaken for large animals. In each instance, the observer is not fabricating an experience. Rather, the brain assembles incomplete visual information into the most striking available interpretation. This process explains why many intelligent, sober witnesses, commercial captains, marine mammal researchers, and recreational divers can genuinely believe they have seen something outside the known fauna. The pattern across both historical and contemporary claims points to a consistent standard in scientific inquiry. Extraordinary assertions, by definition, depart from the accumulated body of verified knowledge. That body includes thousands of hours of fisheries surveys, satellite-tagged whale migrations, deep-sea camera deployments, and coastal monitoring programs that have yet to record any biological signature consistent with a living megalodon. When a claim of such magnitude arises, the expectation is not that every witness must produce laboratory-grade proof, but that the overall body of evidence must eventually include measurable, repeatable data. A single dramatic sighting can prompt further investigation. Sustained absence of supporting traces after decades of scrutiny invites continued skepticism rather than automatic acceptance. This requirement does not dismiss the sincerity of those who report giant sharks. It simply places the burden on the claim itself to meet the same evidentiary threshold applied to every other discovery in marine biology. As we weigh these accounts, it becomes clear that the ocean's vastness and the limits of human perception leave room for honest uncertainty. At the same time, the ecological and fossil constraints we have already reviewed set a high bar for any hypothesis of survival. The next logical step is to examine what satellites, acoustic arrays, and systematic surveys actually reveal when they scan the same waters where these reports originate. Modern ocean monitoring technologies provide one of the clearest windows into whether a creature the size of a megalodon could still move through the seas undetected. Satellite tracking of large marine animals has become routine over the past 2 decades, with thousands of tags deployed on species ranging from great whites and tiger sharks to whale sharks and orcas. These devices record location, depth, temperature, and sometimes acceleration data that stream back whenever the animal surfaces or comes within range of a receiver network. No signal has ever indicated an unknown predator exceeding roughly 20 meters in length. Instead, the tracks reveal predictable corridors along continental shelves, around seamounts, and across entire ocean basins that align with known prey concentrations. A 50-foot shark would generate a signature far larger than any tagged individual, both in physical displacement and in the scale of its required hunting grounds. Yet the cumulative dataset shows no such anomaly. Acoustic monitoring expands that picture across the water column itself. Networks of hydrophones, originally installed for submarine detection and now shared with civilian scientists, listen continuously for vocalizations, propeller noise, and even the low-frequency rumbles produced by large body movements. While sharks themselves are largely silent, their passage through schools of fish or near marine mammals creates detectable disturbances, and any animal displacing the volume of water required by a megalodon-sized body would register on sensitive arrays. Decades of recordings from the Pacific, Atlantic, and Southern Oceans have cataloged everything from blue whale songs to seismic events, yet none contain the rhythmic pressure waves or incidental echoes consistent with an apex predator of that scale. Where unusual low-frequency sounds do appear, follow-up studies attribute them to known sources such as icebergs or distant shipping. The sheer size of a hypothetical surviving megalodon makes detection almost inevitable under current capabilities. At roughly 15 meters or more, such an animal would outmass the largest great whites by an order of magnitude and would need to consume hundreds of kilograms of prey daily. That requirement alone would leave a measurable footprint in acoustic backscatter from prey aggregations and in the movement patterns of tagged marine mammals that suddenly alter course or dive deeper. Tagging studies of great whites illustrate the point directly. Individuals equipped with pop-up satellite tags have been tracked from California to Hawaii and from South Africa to Australia, revealing transoceanic migrations that follow temperature fronts and seal colonies. These journeys are logged in fine detail, including repeated dives to several hundred meters. No equivalent tracks exist for anything larger, and the absence is telling because the same tagging programs would almost certainly encounter or be displaced by a dominant predator of megalodon proportions if one were present. Naval sonar and submarine observations add another layer of scrutiny that operates independently of biological research. Military vessels patrol the same deep channels and trenches where a relict population might theoretically hide, using active and passive sonar that can distinguish objects the size of a school bus from background noise. Historical logs and declassified reports contain numerous detections of large marine animals, almost all later identified as whales or whale sharks, through corroborating visual or acoustic data. Unexplained contacts are investigated precisely because they could indicate submerged hazards, yet none have ever matched the profile of an unknown 50-foot shark. Submarines operating at depth have passed within meters of great whites without registering anything anomalous, underscoring that even well-known species are routinely cataloged rather than overlooked. Citizen science and drone footage extend this surveillance into shallower waters where most eyewitness reports originate. Recreational fishers, divers, and coastal residents now upload high-resolution video almost daily from regions once considered remote. Smartphone apps allow rapid sharing of sightings, and drone operators routinely survey surf lines and bait balls for hours at a stretch. While these platforms have documented rare behaviors such as breaching white sharks or massive whale shark aggregations, they have not produced verifiable footage of anything approaching megalodon dimensions. When ambiguous shapes appear, multiple angles and follow-up dives usually reveal basking sharks, floating debris, or known species viewed under distorting surface conditions. The democratization of imaging has therefore tightened rather than loosened the constraints on speculation. Limitations remain honest and worth stating plainly. The deep ocean is still incompletely mapped, and vast stretches of the abyssal plain receive only sporadic acoustic coverage. Satellite tags eventually detach, and not every animal can be tagged. Military sonar data are not fully public, and some regions experience less traffic than others. These gaps leave theoretical room for undiscovered species of moderate size. Yet the combination of satellite telemetry, continuous acoustic arrays, naval patrols, and widespread public imaging creates overlapping coverage that grows denser each year. A predator requiring the caloric intake and physical presence of a megalodon would need to evade every one of these systems simultaneously across multiple ocean basins, an increasingly improbable scenario as the datasets lengthen. The fascination with monster sharks persists because the ocean retains its mystery, and because occasional misidentifications keep the possibility alive in popular imagination. At the same time, the objective record from these technologies shows consistent patterns that match only the species we already know. That record does not close every door, but it raises the evidentiary threshold for any claim of survival to a level that scattered sightings alone have not yet met. As monitoring networks continue to expand, the same tools that track known migrations will also serve as the most reliable test for anything still hidden beneath the surface. Welcome back to our deep dive into whether the megalodon could still exist somewhere in today's oceans. Comment where you are in the world and what time you're seeing this as we continue weighing the evidence. Building directly from the monitoring data we just examined, Many viewers wonder if comparisons to rediscovered species might change the picture. After all, science has a track record of declaring animals extinct only to find them alive and well. Let's examine those cases carefully and see why they ultimately fall short as analogs for a surviving megalodon. The coelacanth stands as the classic example, thought to have vanished at the end of the Cretaceous 66 million years ago. A living specimen turned up in a South African fish market in 1938. Subsequent populations were located in deep caves along the Indian Ocean and later in Indonesian waters. These fish reach about 2 meters, inhabit steep rocky slopes between 100 and 500 meters, and feed on smaller fish and cephalopods. Their rediscovery showed that certain deep, stable environments can preserve ancient lineages with minimal fossil representation. Yet the coelacanth's small size, low metabolic rate, and cryptic habitat allowed it to remain hidden for decades. Giant and colossal squids offer another frequently cited parallel. Both were long known only from beaks found in whale stomachs and occasional washed-up carcasses. The first confirmed live giant squid footage came in 2005, and colossal squid observations followed through trawls and submersibles. These animals inhabit the mesopelagic and bathypelagic zones, can exceed 10 meters in total length, and avoid surface waters. Their rediscovery reinforced that vast dark ocean layers still hold surprises. Even so, both species leave physical evidence, floating beaks, sucker scars on whales, and occasional strandings that scientists could trace long before cameras captured them alive. What these cases actually teach us is valuable. They demonstrate that the fossil record is incomplete, especially for soft-bodied or deep-dwelling organisms, and that remote habitats can shelter relict populations. They also remind us to stay open-minded when evaluating claims of survival. At the same time, the differences with Megalodon are fundamental. Megalodon reached roughly 15 to 20 meters and possessed a metabolism likely closer to that of great white sharks or lamnids, requiring hundreds of kilograms of prey each day. Coelacanths and giant squids occupy much lower trophic levels and far smaller body masses, allowing them to persist on limited resources in confined spaces. Habitat and size factors further separate these examples. The coelacanth's cave systems and the squid's midwater depths are geographically restricted and difficult to survey comprehensively. A megalodon-sized shark would need expansive hunting grounds spanning continental shelves and open ocean basins to sustain its caloric demands. Its passage would disturb prey schools on scales visible to acoustic arrays and satellite-tagged marine mammals, patterns we simply do not observe. Rediscovered species also tend to be invertebrates or modest fish whose skeletons or bodies preserve poorly. Whereas megalodon teeth are among the most durable and commonly fossilized structures in the ocean, their total absence from post-Miocene deposits is therefore far more telling. Lazarus taxa comparisons ultimately fail for megalodon because they ignore ecological scale. A lone coelacanth or giant squid can hide. An apex predator the size of a city bus cannot. Its presence would restructure entire food webs, leaving measurable gaps in whale migrations, seal colony health, and fishery catch data, none of which appear in modern records. While the rediscoveries of the coelacanth and large squids rightly encourage humility about what the deep sea might still conceal, they also highlight why megalodon survival would require an entirely different and far less plausible set of circumstances. The same principles that allowed those smaller species to evade detection for so long work against the idea of an undetected megalodon. Even as the ecological barriers to megalodon survival appear insurmountable based on prey demands, habitat scale, and the total absence of modern traces, popular culture keeps the possibility alive in vivid detail. In this section we examine how films, television, and other media depict the giant shark against the backdrop of verified paleontology, and why those portrayals continue to resonate. Comment where you are in the world and what time you're seeing this as we weigh entertainment against evidence and consider what keeps the legend circulating. The 2018 film The Meg introduced millions of viewers to a 23-meter-long predator rising from the Mariana Trench to terrorize the surface world. Earlier movies and novels have shown similar versions of the species as an almost supernatural force capable of swallowing boats whole. These dramatizations draw loose inspiration from the fossil record of teeth and vertebrae, yet they compress millions of years of evolutionary history into a single living monster that behaves more like a cinematic villain than the real apex predator whose extinction coincided with the loss of large marine mammals at the end of the Pliocene. Shark Week programming has added another layer. The 2013 mockumentary Megalodon, The Monster Shark Lives, presented staged footage and actor interviews as though scientists were actively debating fresh sightings. The special drew record ratings but prompted swift corrections from marine biologists who pointed out that no acoustic, photographic, or genetic data supported the claims. Subsequent programs adopted clearer disclaimers, yet the initial broadcast illustrated how easily dramatized content can outpace careful explanation. Media portrayals shape public perception by filling the information gap with emotionally compelling images. When audiences see a massive dorsal fin slicing through waves or hear dramatic narration about unexplored trenches, the idea of survival feels plausible, even though every verified megalodon fossil dates to at least 3.6 million years ago. The result is a persistent undercurrent of hope that somewhere the species endures, fueled less by new discoveries than by repeated exposure to the monster narrative. Scientists have responded with measured pushback rather than outright dismissal. Paleontologists and shark researchers routinely publish summaries of the tooth record, stable isotope data on diet, and oceanographic surveys that show no room for an undetected population of that size. Their critiques focus on the absence of physical evidence rather than attacking audience curiosity, underscoring that the fossil timeline and ecological requirements leave little room for reinterpretation. Still, monster narratives hold undeniable appeal. They tap into a long-standing human fascination with ancient giants and the hidden ocean, offering a sense of wonder that pure data sometimes struggles to match. Viewers are drawn to the possibility that nature still harbors something larger and older than anything cataloged, a feeling that echoes across cultures and generations. This tension creates real challenges for responsible science communication. Writers and educators must convey the strength of the consensus without sounding dismissive of the very curiosity that brings people to marine biology in the first place. Framing the discussion around what the evidence does show, the remarkable diversity of living sharks, and the genuine mysteries that remain in the deep sea allows the conversation to stay engaging while remaining accurate. Belief in a surviving megalodon persists not because new data supports it, but because the story satisfies an emotional need for the unknown that factual accounts alone have not yet replaced. In this section, we lay out the strongest ecological arguments showing why megalodon survival is effectively ruled out by the structure and monitoring of today's oceans. Comment where you are in the world and what time you're seeing this as we weigh each line of evidence and see how they converge on a single conclusion. Modern ocean ecosystems are among the most intensively studied environments on the planet. Decades of ship-based surveys, satellite tagging, acoustic arrays, and fishery-independent monitoring programs have mapped the distribution, abundance, and interactions of marine megafauna from the surface to the abyssal plain. These datasets reveal consistent patterns. Every large predatory niche is already occupied by well-characterized species whose movements, diets, and population trends are tracked in near real time. Introducing a 15 to 20 meter apex predator the size of Megalodon would require wholesale rearrangement of those patterns. Yet no such rearrangement appears anywhere in the record. Apex predators leave unmistakable ecological fingerprints, They structure food webs through direct predation and through fear-mediated effects that alter the behavior of prey species across entire basins. Great white sharks, orcas, and sperm whales each generate measurable signatures in stable isotope ratios, stomach content archives, and telemetry tracks. A surviving megalodon would exert comparable pressure on the same prey fields, yet none of the long-term monitoring programs that follow tuna pinnipeds or large cetaceans show any unexplained mortality spikes or behavioral shifts that would indicate an additional super predator. The absence is not a matter of insufficient effort. It is the positive result of systematic observation. Population genetics adds another independent constraint. Long-lived, slow-reproducing species such as sharks accumulate low genetic diversity when population sizes remain small for many generations. Ancient DNA extracted from megalodon teeth already shows that the species maintained healthy genetic variation until its final decline, implying historically large numbers. A remnant population persisting for 3.6 million years would have passed through repeated bottlenecks, producing detectable reductions in heterozygosity and elevated inbreeding coefficients. Modern shark genomes, by contrast, display the diversity profiles expected for stable, openly breeding populations. No cryptic megalodon lineage has surfaced in any of the global barcoding initiatives that routinely turn up previously unknown elasmobranch species. Minimum viable population requirements reinforce the same point. Demographic models for sharks indicate that sustainable numbers for a species of megalodon's size and metabolic demand would need to number at least several hundred reproductively active adults and more probably several thousand to buffer against stochastic events. Such a population would consume thousands of tons of high-calorie prey annually. Even if the sharks adopted an extremely low-energy lifestyle, the biomass removal would register in fishery statistics and in the body condition of overlapping predators. No such signal exists. Claims that a handful of individuals could persist indefinitely overlook the well-established thresholds below which extinction becomes deterministic. Environmental DNA sampling supplies perhaps the most direct test. Water and sediment samples collected across every major ocean basin routinely recover DNA from sharks ranging from pygmy species to whale sharks. Megalodon, if present, would shed orders of magnitude more cellular material than these smaller relatives. Yet exhaustive eDNA surveys targeting the deep scattering layer, Hadal trenches, and continental slopes have returned 0 megalodon sequences. The same filters that capture great white and short-fin mako DNA would capture megalodon DNA. Its consistent absence is therefore informative rather than inconclusive. Counter-arguments sometimes suggest that the species could occupy an ultra-specialized niche invisible to conventional surveys. However, the same oceanographic models that map prey density also map the physical conditions required to support a warm-blooded giant. Those conditions overlap extensively with regions already sampled at high resolution. Moreover, any viable population would still need to reproduce, and reproduction in sharks produces detectable nursery signatures in nearshore or slope habitats. No such nurseries have appeared in fossil or modern records after the Pliocene. The weight of cumulative evidence therefore rests on convergence rather than any single smoking gun. Fossil timelines, prey demand calculations, genetic expectations, minimum population thresholds, and molecular detection methods all point to the same outcome. Megalodon no longer exists. Each line of evidence was gathered for independent scientific purposes, yet each independently excludes a living population. When multiple unrelated datasets align so cleanly, the remaining probability of survival drops below any reasonable threshold for continued speculation. This does not diminish the genuine mysteries that still exist in marine biology. New shark species continue to be described, deep-sea behaviors remain only partially mapped, and climate-driven changes are reshaping distributions in real time. Those frontiers are precisely where research effort is now concentrated. The ecological case against megalodon survival simply clears the ground so that attention can shift to living species whose conservation needs are urgent and documentable. In doing so, the same rigorous standards that closed the door on one ancient giant open clearer windows onto the sharks that still patrol today's oceans. As we bring our journey through the evidence for and against a living megalodon to a close, this final section steps back to consider the deeper lessons this extinct giant offers us. Comment where you are in the world and what time you're seeing this as we reflect on extinction, climate parallels, and why protecting today's sharks matters more than chasing ancient legends. Extinction itself stands as one of Earth's most consistent natural processes, not an aberration but the default outcome for the vast majority of species that have ever lived. Megalodon's disappearance roughly 3.6 million years ago fits squarely within that pattern, like the dinosaurs before it, or countless marine reptiles that vanished at the end of the Cretaceous. The shark simply could not adapt quickly enough when its world changed. Paleontologists trace this to a combination of cooling oceans, shifting prey populations, and competition from emerging predators such as early great whites. The fossil record shows a gradual decline rather than a sudden catastrophe, underscoring how even the largest animals remain vulnerable when environmental conditions move beyond their physiological tolerances. Those same environmental pressures invite direct parallels with the climate shifts underway today. During Megalodon's final centuries, sea surface temperatures dropped several degrees as the Pliocene transitioned toward the Pleistocene ice ages. Coastal upwelling zones that once supported massive schools of fish and marine mammals contracted or relocated, starving the energy demands of a warm-blooded superpredator. Modern warming trends are reversing parts of that process in some regions while triggering entirely new disruptions elsewhere. Coral bleaching events, deoxygenated dead zones, and poleward migrations of prey species. The lesson is not that history repeats exactly, but that large, slow-reproducing sharks have narrow windows of tolerance. When those windows close, even apex status offers no guarantee of survival. That recognition drives urgent conservation priorities for the sharks still with us. Species such as the great white, short-fin mako, and whale shark now face threats that echo the pressures once faced by megalodon. Targeted fisheries, bycatch and longline operations, and habitat degradation from coastal development. Unlike their extinct relative, however, these sharks benefit from real-time monitoring, international trade regulations under CITES, and marine protected areas that can be expanded as data improve. Paleontological insights into Megalodon's life history, its slow growth rates, late maturity, and reliance on specific nursery habitats, help biologists model recovery timelines for living populations. When we protect the shallow bays and seamounts these species need for reproduction, we are applying lessons written in ancient teeth and vertebrae. Yet the wonder of what once existed remains undiminished by its absence. A 15 to 20 meter shark capable of taking down baleen whales represents one of evolution's most spectacular experiments in size and power. Standing before megalodon fossils in museum halls, visitors often feel a visceral awe that no CGI rendering quite captures. That sense of scale reminds us how dynamic and inventive life has been across deep time. Even if no living individual patrols the oceans today, the species' 20 million year run across nearly every tropical and temperate basin stands as testimony to the productivity of ancient seas and the adaptability of cartilaginous fishes. Mystery itself retains value even when survival is ruled out. The persistent questions surrounding Megalodon have spurred public interest in marine paleontology, encouraged citizen science fossil hunts, and funded expeditions that turned up new species of smaller sharks and rays along the way. Speculation about hidden populations, however improbable, has prompted deeper acoustic surveys and eDNA campaigns whose datasets now serve multiple unrelated research programs. In that sense, the myth has been productive, It keeps audiences engaged with the scientific process long enough to absorb the harder truths about extinction and conservation. Paleontology, in turn, supplies concrete guidance for marine management. Tooth morphology reveals dietary flexibility that informs fisheries models. Isotopic signatures in enamel record ancient temperature ranges that calibrate current climate projections. Population level size distributions from fossil sites highlight the importance of preserving age-structured communities today. When managers set catch limits or design migration corridors, they draw on the same comparative methods that established Megalodon's timeline. The discipline therefore bridges deep history and present action, turning extinct giants into reference points for keeping modern oceans intact. Ultimately, the story of Megalodon does not end in disappointment over a lost monster, but in renewed appreciation for the living world we can still influence. Its extinction illustrates the irreversible consequences of environmental thresholds crossed too quickly. Its fossil legacy equips us with knowledge to avoid repeating those thresholds for species that share our planet right now. By supporting sustainable fisheries, expanding protected areas, and reducing carbon emissions that acidify and warm the seas, we honor the memory of the largest shark that ever lived, not by hoping it still swims unseen, but by ensuring its modern relatives continue to thrive. In that effort lies both scientific responsibility and a quiet form of gratitude for the extraordinary life that preceded us.